So let's begin with lecture 14, and today we will do three kinds of integration. The beginning one is the triple integral, and then we'll do two surface integrals. One is the usual surface integral of a scalar field, and the other one will be flux integral, which you have seen for in 2 dimension flux across a curve, and in 3 dimension it will be flux across a surface. So those two later. So let's talk about triple integrals. So now we are going to integrate a function. So let's take a function f which is defined on some region V, subset of R3 to R, and what we need is just continuity of this function. So it's a scalar field FB continuous. So we want to define what is meant by the integral of f over this region V. So we want to define V. Let's take V be a bounded region, so it doesn't shoot up to infinity. So we want to define integral of f on V dx dV. The integral of f over the region V. So the definition is very much like what we saw in 2D. So let's start with the picture. So I have a certain region in 3 dimensions. And how do I see this? I want to see this. Maybe I'll draw a picture bit later. So my idea, the idea, mimicking the idea of how we define double integrals, we want to take a partition, but now the partition is not in. So let me see, in 2 dimensions we had a region in the plane, and we took a partition of the region by rectangles. You take, suppose these are the boundaries in the x component of the region, and these are the boundaries of the component in the y, boundary of the region in the y component. Then you take a partition of the interval AB, partition of the interval CD, and that way you get a partition of the region in terms of the squares or rectangles, not squares. Now similarly, we'll take a partition. So let's call this region in the xy plane AB, this region as CD, and we are going to make a partition of the x-axis, y-axis and z-axis, and I will get a typical piece here. And now I have a function on this. So I want to define a function. I want to define an integral. So I have a function on this region. This region, let's suppose, is this blob. Then I take a column and I'm going to make a partition of my z-axis as well. That's a good enough picture, isn't it? And then my region for z-axis would be something like this. Sits between, say, E and F, and I make a partition here. So that way I will get a partition of this column into bits of cubes. So this is a typical cube, and this I will write as, say, it's the set of points x, y, z, such that your x is between xi and xj, y is between y, what should we call it, k and y, xi and xi plus 1, not xj, y is between yz and yz plus 1, and z is between zl and zl plus 1. So this is a cube. I call this cube QIJL. And then the idea is you form a lower sum and the upper sum Or another sum you can form is by the way you can form is by taking a point. So consider a partition of V into cubes Qijl. Maybe I will not separate them by commas. Let's just write down Qijl, and I goes between 1 and n, j goes between 1 and m, and l goes between 1 and p. And then I take function's value at any point. So let psi I j l be any point in this cube, and form the sum function's value at psi I j l times the volume of Qij l, and you take the sum over I, j and l. I goes between 1 to, or maybe we can write this as a triple sum if you want. So my I goes from 1 to n, j goes from 1 to m, l goes from 1 to p, f psi I j l, volume of the cube Qij l, and let's call this sum SPF. Just like you could form also lower sums and upper sums. The point is, as the partition is made finer and finer, all these limits exist and they are equal, and that will be called the triple integral of f. So this is a result. This again you will prove in advanced calc as norm of p tends to 0, that is the partition is made finer and finer. That means your nm and p tend to infinity, and the grid of the partition becomes smaller. So that is the partition becomes finer and finer. That's the correct word to use. As the partition becomes finer and finer, limit of SPF as length of P tends to, length of P will be measured as, so I will define quickly what is the length of P. Is the maximum of the volume of Qijl, where I varies over 1 to n, j varies over 1 to m, and l varies over 1 to p. So that's the length of the, that's called the norm of the partition. As the norm tends to 0, this limit exists and is called the triple integral of f over the region V, and is denoted by three integral signs: V, F, X, dV. Good. So now this question is again, as in the case of double integrals, how to find it, how to compute, because this definition is of no use when it comes to computation. So how to compute this triple integral f dv. So now, just like in the case of two variables, we will have regions which are of type 1, type 2, type 3. We will see, we will only work with type 1 regions. So the region is type 1 if the volume V is sandwiched, it looks like a hamburger. Now it's a real three-dimensional hamburger. So it is the region in between graphs of two functions, z equal to phi1y xy, and this is the graph of z equal to phi2 xy. So the result is theorem. Suppose, so I'm going to make an assumption, and let me complete this picture first. Let's drop a perpendicular, let's drop a projection, and this is your region D in the plane. So suppose the region V is given by V is equal to xyz such that my z is lying between phi1x y and phi2 xy, and my xy vary over D. Here phi1 and phi2 are two continuous functions. Phi1, phi2 are continuous functions of two variables, continuous maps on D. D is the projection of V on the xy plane. Then in this situation, triple integral of f over the volume V is going to be, what you do is you integrate the z variable out. So in other words, you are picking a point, fix xy in D, and you are integrating it from this point to that point, and then you move your xy over the entire region D. So this is your phi1 xy, this is your phi2 xy. So you integrate out z from phi1 xy to phi2 xy, and then you get a function only in terms of x and y, and then you take its double integral over D with respect to A. So this is the theorem. This is how this converts triple integral into, finding a triple integral into computing repeated integrals. So this formula converts the problem of computing a triple integral into a problem of finding repeated integrals. Because you know how to write a double integral in terms of repeated integrals. So let's see some examples. So let's look at, for example, let's take a function which is, say, so problem 1. Find the triple integral of x dv, where V is the region, or V is the volume, or region is a better word, right? Bounded by planes x equal to 0, y equal to 0, z equal to 0. These are the x, y, z planes. And the other last plane is 3x plus 2y plus z equal to 6. So as usual, the very first thing is drawing a picture. First draw a sketch of this region. So now that's not too difficult. You know how to draw the plane. This plane 3x plus 2y equal to z, you will see when y and z is 0, x is 2. So it cuts the x-axis at 2, 0, 0. When x and y's are 0, z is 6. And when x and z are 0, y is 3. So this is the plane which looks like that. And then the other bounding planes are the x and y and z, x, y, y, z and z x planes. So this is the region. This is your V. So first thing is you want to understand the projection. So what is D? The projection of V on the xy plane. That's going to be a triangle. As you can see, it's this triangle. So this region is going to be, and what's the equation of the line, which is this edge? This will be, your equation of the plane is 3x plus 2y equal to plus z equal to 6. So you put z equal to 0. So this line is 3x plus 2y equal to 6. So this line is 3x plus 2y equal to 6. So this point is going to be when y is 0, x is 2. And when x is 0, y is 3. So that's going to be our D. So now you see that this region is bounded above by the surface z equal to, so this V is bounded above by z equal to 6 minus 2x minus 3y. That was the equation, right? Minus 3x minus 2y, I think. 3x minus 2y. And below by the xy plane, which is z equal to 0. So therefore, and your function f of x, y, z is x. Here our function is x, isn't it? That's what we have to integrate. Yeah. So what do we get? So therefore, integral of x dv over v will be, you first integrate this function as a function with respect to z, from the lower limit to the upper, z equal to 0 to the upper surface is z equal to 6 minus 3x minus 2y. And then whatever you get will be only in terms of x and y, which you integrate as a double integral on this triangular region. So what will that be? Now if you are integrating on the triangular region, this is of type 1. You can see this region as region of type 1. So you integrate 0 to, the top will be 6 minus 3x by 2. That's the curve y equal to 6 minus 3x by 2. Now let me write the inner thing. This is 6 minus 3x minus 2y x dz. Then this is dy, and then at the end you get dx, and x will go between 0 to 2. So then you start working from inside. The rest is simple. 6 minus 3x by 2. Integral of xz is, x dz is x times z, and that will be between 0 to 6 minus 3x minus 2y dy, and then dx. So this is going to be integral 0 to 2, integral 0 to, maybe I'll write this as 3 minus 3 by 2x. And then evaluating between these two limits will give you x times 6 minus 3x minus 2y. X times 0 is 0. So this dy, and then you have dx. So this is integral 0 to 2. Now you can see that 6 times this is independent of y. So this I will write separately. 6 minus 3x times y, because you are integrating this function 6 times x times 6 minus 3x, which is independent of y. And then you will have 2x 2 times x, and the integral of y will be y squared by 2. And this will be evaluated between 0 to 3 minus 3 by 2x dx. This 2 and 2 will go away, and you will get 0 to 2. And now my y, this is going to be x 6 minus 3x times y will be 3 minus 3 by 2x. The value at 0 is 0, minus xy square, which is 3 minus 3 by 2 x square. The value at 0 is 0. So this is going to just say long computation, but it's not impossible to do. Let us simplify this a little bit. How do we do this? Maybe it is better to pull out this. So again, I will write this as 6 minus 3x by 2. That's a common factor multiplied by this, which is 6x minus 3x square, minus you will have x times 3 minus 3 by 2x dx. So 1/2 integral 0 to 2 6 minus 3x good. And then inside, what do you get? Yeah, so I should get, so I have multiplied by, I have taken out 2, so that's how I get 6 minus 3x, which I multiplied by x, so I got that. So I get 6 minus 3x square minus 3x plus 9 by 4, sorry, 3 by 2 x square. 3 by 2 x square, right? So let me pull out a 3 from here. This is 2 minus x into bracket. So what do we get? We get 3x and minus 3x square plus 3 by 2 x square. 3 minus 3 by 2 is minus 1/2 minus 3 by 2, isn't it? And that is going to be, so let's pull out a 3 and let's multiply by 2 and pull out a 3. So that will give me 9 by 4 integral 0 to 2 2 minus x times I will get 2x minus x square, because I have taken 3 out and then I make the denominator the same, so I get 2x minus x square. So this is 9 by 4, 0 to 2, and then let's just multiply. You get 4x minus 2x square minus 2x square plus x cube. So when you integrate this, you are going to get x square by 2x square, because this is x square by 2, that 2 cancels, you get 2 by 3x cube. 4 by 3 actually, these 2 will give me 4x square, integral is 4x cube by 3 plus x to the 4 by 4 between 0 to 2. So it's 9 by 4, value at 2 will be 8 here, minus 2 cube is 8, 8 times 4 is 32, and 16 by 4. So that's going to give you 9 by 4 times whatever it turns out to be. I will get 8 times 3 is 24, 24 times 4 is 96, minus 64 times 32 is 128, and 16 times 3 is 48 by 12. So that gives me, if I cancel 3, I get 1 over, you will be left with 3 here and 4 here, so it will be 3 over 16, and then this turns out to be 144 minus 16, minus 128 is 16, so the answer should be 3. So that's how you evaluate triple integral. The last thing was a little bit long, but it is not a difficult problem because the integration was just Calc 1 integration. Nothing difficult about that. Let's do one more. Let me try to do it when your surface is, let me pick something like trying to find a good problem on triple integrals. Let's see. Okay, so here I have something. Yeah, let's look at I have to make sure that I shouldn't ask you something which I have asked on the homework. So one more second. I would like to see what your homework assignment is. Okay. Let's find out so let's write problem 2. Yeah, find the volume. By the way, so if the function f is 1, identically 1, then the meaning of the triple integral is it just measures the volume of the region. So I will formulate it this way. Find the volume of the region bounded by the plane z equal to 1 above and the cone z equal to root of x square plus 1, x square plus y square below. So let's look at, so use triple integral. So the idea is, first you draw a sketch. This is the cone z equal to x root of x square plus y square. At z equal to 0, you have x and y both 0. And now z is equal to 1. This is the plane above. So you want to find the volume of this region. So this is your v. So what you need is the projection of this region on the xy plane. That's your d. So you see, when z is 1, your x square plus y square root is 1, and that means the projection of this region on the xy plane is just the disk with radius 1. Is the disk with radius 1. So therefore volume is equal to the triple integral of the function v of function 1 on this region v. So let's write this as a triple integral as a repeated integral. So this is going to be, the lower function here is the z equal to 0. The upper function is the lower surface is z equal to root of x square plus y square. Let me get the eraser. So the lower function is z equal to root x square plus y square. The upper function, surface is z equal to 1. Function is 1. Then you get dz, and this you will integrate over the region D as a double integral. So this is going to be integral, and now let me write down, this is going to be just integral of z. Integral of 1 is z, and this z will be evaluated between these two limits, dA over d. And I bet that this is going to be much easier if I write it in polar coordinates. So we want to compute 1 minus root x square minus y square over the unit circle, and so use polar coordinates. So I will write this as 1 minus root r square, so which is r actually, r dr d theta. R goes between 0 to 1, theta goes between 0 to 2 pi. So this gives you integral 0 to 2 pi. Integral of this thing is integral of r minus r square, and that will be r square by 2 minus r cube by 3, 0 to 1 d theta. And so that's going to be integral 0 to 2 pi, and then you get 1/2 minus 1/3 minus 0 minus 0. That's 1/6. And that's going to be 2 pi by 6, which is pi by 3. So the volume of this cone is going to be pi by 3. Yeah. So that was your second problem on triple integrals. Now let me move on to, because I would like to finish these 3 different integrals which are not much different. The evaluation of these has a common feature, namely common part is we convert this into finding the double integrals, which you have had practice with. So let's now look at the concept of surface integrals. So let me try to introduce what these are. Okay, so now we are given a surface in 3D, which is this cap, sigma. I'll call it sigma is the level surface of function f of xy. So the equation of this is z equal to f of xy. Projection of this is d. Maybe I'll draw a little, that looks more like its projection. This is your d. So now you have a function g on this. So I should formulate it this way. Let sigma be a level surface of F more precisely. I want to take sigma to be the set of all points x, y, z such that z is f of xy and xy varies over D, where D is the projection of sigma on the xy plane. And now I have a function, scalar valued function g, which is defined on sigma with values in R. So G is a scalar field on sigma. And then we want to assign the meaning to integral of G on the surface sigma. We want to define what we call a surface integral of G on sigma, denoted by its double integral sign again, but now you are not integrating on a region which is in the plane, but this is a curved surface. So this is double integral over sigma G of x, y, z ds. Here S stands for, rather than A, I could put A here also, but S is more conventional. S stands for the surface. So I have a function on this. So G is a function which takes values from sigma to R. And now I want to integrate this function on this cap. So how does this go? So the idea is simple. Let me draw again the picture. I'm going to partition, and now when I take a partition of my D, it induces a partition of the surface. This we have seen when we found the formula for surface area. So I take a typical rectangle here. This is my xi plus 1, yz plus 1, and this rectangle, if you look at the picture, so this gives you this little cap, little piece on the cap. What should we call it? This we call Riz. I don't remember whether we call that R. Let me call this thing Riz. Yeah. So again, take a partition which is going to be, how should I get a partition? Partition P, which is going to be A equal to x0 less than x1 up to xn, which is B, cross C equal to y0 less than y1 up to ym equal to D. So these are my, this is my A and this is my B. That's going to be my partition for the y extended C and D. And so you get a partition. So consider partition of the region D. So this induces a partition of the surface sigma, by the images, by I will say Riz, the image of the rectangle xi plus 1 cross yz plus 1 under the function f. So what you are doing actually, you are taking this is your rectangle, and its image under the function f is what you have, which is this Riz. So in other words, Rij is going to be the set x comma y f of x y, and where my x comma y vary inside xi plus 1 cross yj plus 1. So that's how I get a partition of the surface, and then we form the sum. We pick any point xi ij inside Rij and form the sum So what will we do now? We will take the value of g at xi ij multiplied by the area of Rij and then sum over I equal to 1 to n, j equal to 1 to m, and this we will call SPG. Function is g, which we are integrating now. And then again, as norm of p tends to 0, limit of SPG converges. This limit exists, and this limit will be called the surface integral of g on the surface sigma. This limit is called the surface integral of g over surface sigma. And now how do you find it? So actually you have so now note that, and this is where I ask you to go back and look at how the formula for area of a surface was derived. Note that Rij, the area of Rij, we verified that this was very close to root 1 plus fx square plus fy square times area of the rectangle. So it is xi plus 1 minus xi, magnitude of this, times yj plus 1 minus yj, which is this factor 1 plus root of 1 plus fx square plus fy square times area of the square or of the rectangle, xi plus 1 cross yj plus 1. Why this factor comes up is exactly the reason is same as in the proof of finding the formula for area. So actually, using this, you see that we see that SPG is going to be summation g of xi ij times root 1 plus fx square plus fy square. Yeah. And I call xi, this is times area of the rectangle. I should give a name to this rectangle. What should we call this rectangle? Xi minus xi to xi plus 1, yj to yj plus 1. Maybe we'll call it the rectangle Cij. And so now I pick, see, this is the picture. I'm picking a point here which I could have thought of as a point on the base. So if I pick psi ij here, this will be written as f of eta ij on the base. So this will be summation f of, this will be g of f of eta ij times root 1 plus fx square plus Fy square times area of Cij. But then you see that this limit, this will converge to the double integral of G composition F on the region D, which is xy, so this is a two-dimensional region, times root of 1 plus fx square plus fy square dA. So this formula tells you how to actually compute. So this gives us a formula for finding so in other words, I made a little, this has to be interpreted as g of xy f of xy, because your z is f of xy. So when I say G composition F, what I mean is this. So this gives you a formula for finding the surface integral. Good. So let's do one problem to practice. So let me write down the formula one more time. So if you want to integrate G ds on a surface sigma, this is going to be a double integral on D. D is the projection of S. G of x, y, z. Z will be f of xy times root of 1 plus fx square plus fy square dA. So problem number 3. Let's see how to do this. Let's take yeah. So let's say find surface integral of G of xyz on sigma ds, where G of xyz is simply, let's call it xyz, why not? This is a function of 3 variables, and sigma is given by xyz such that z is 1 minus 1 half x square plus y square. X is between 0 and 1, y is between 0 and 1. So always as before, first step will be first draw a picture. Sketch of sigma and D. So now you see that this surface is going to be, this is something you should be able to see. It's a parabolic cone. When z is 1, x and y should be 0. That's when z is 1. When x square plus, when z is 0, x square plus y square is 2. So that's a circle of radius 2. Let me draw a better one. And so it is going to be something like this. This is x square plus y square equal to 2. This is 0, 0, 1. And now I'm taking x and y between 0 and 1. So I'm taking a square here. And I'm looking at the patch which you get here on the top. Do you see this patch? This is a better picture. So that's my sigma, which is above d, and this is my d. So my d is going to be the unit square, and on this d, on this sigma, you are integrating the function x, y, z. Good. So what is the little f in our problem? So here f of x, y, which is this function z, which is given to be 1 minus half x square plus y square. So we'll need to calculate fx and fy. Fx is going to be differentiate this, so minus 2x by 2, which is minus x. Similarly, fy will be minus y. So this quantity 1 plus fx square plus fy square will be root of 1 plus x square plus y square. Good. And then I'm integrating the function x, y, z times this thing 1 plus fx square plus fy square over the region A or D, dA over the region D, R integral equals this. And now I want to just write down my z. Z was, to make life a little easier, I can change my function slightly. Should I do that? Probably not. It doesn't matter really. It is going to be xy times 1 minus half x square plus y square times root 1 plus x square plus y square dA. And integrating this is not a problem, it just takes time. Integral on this a is not difficult. This is a square, so I will integrate with respect to, so let's write this down, 1 minus x square plus y square by 2 times root of 1 plus x square plus y square dy and then dx. Now integrating with respect to y will test us a little bit, isn't it? So this will be integral 0 to 1 xy times root 1 plus x square plus y square dy then dx minus minus, then you are going to multiply these three things. So minus, you are going to get, this will take a long time, and so I should have thought about choosing a suitable z. So what will I do to choose a suitable z? I could check, I could take z to be 1 minus, I could take the function to be yes, let's try to take the function 1 minus root z. I mean my function g, hold on. So let's take this function g to be, so to make the integral a lot easier, let's make this function root of 1 minus z. Good, then life will be a lot easier. Then my function here is my z. The function is not z, but it's now 1 minus, so let me rewrite this. So our function is x times y times root of 1 minus z. So if I replace, so let me do that here. So if I take root of 1 minus z, what do I get? So I have z is 1 minus half x square plus y square. So you get 1 half x square plus y square equal to 1 minus z. So if I take the square root of that, then I get 1 over root 2 times, no, so let me make it, I would like to get 1 plus x square plus y square. How do I get that? So what should I do? Because then the problem will be a lot easier. To get 1 plus x square plus y square, I should choose, so I want 1 minus z is that, so if I make this 2 times that, I get, so let's make the function to be 1 plus 2 times 1 minus z. That would give me, if my z dependence is this, then that would give me 1 minus z is going to be just x square plus y square. Yeah, so that would be better. So let me change the problem by having this function to be having this as x times y times, what did I say here? 1 plus 2 times 1 minus z. So 1 plus 2 times 1 minus z. So if I take that as my function, then my problem will be, here I will have to replace this function by 1 plus, so it is x y into bracket 1 plus 2 times 1 minus z, and so let me clean up the rest. And then this will turn out to be simply double integral on d, which will be integral from 0 to 1, y 0 to 1, this is xy, and 1 plus 2 times 1 minus z will simply turn out to be, see, 1 minus z will turn out to be 1 half x square plus y square. So if you multiply by 2, this gives you x square plus y square, and then that 1 plus that will give me, to make life even easier, I could take its square root. So then I will get, yes, I could take its square root. So let me change the function. So then I will just simply get root of 1 plus x square plus y square. And then I will get another one. So I designed my function g this way. So our integration becomes easy. So what I want is not 1 plus 2. By the way, this is exactly 3 minus 2z. So I take the square root of that. So let's change this problem to, so this is how you design problems, square root of 3 minus 2z. So if I take square root of 3 minus 2z, then you see that you can check that square root of 3 minus 2z will simply be root 1 plus x square plus y square. Check this. But then our integration will be much easier because our radical signs will go away. You will get xy times 1 plus x square plus y square. This you can integrate very easily. dy and then dx. So this is integral 0 to 1. Integral of xy will be xy square by 2. Integral of x square y cube will be x square y square by 2. X cube y cube by 2. And the other integral is x y cube, which will be y to the 4, y to the 3. So it will be y to the 4 by 4. 0 to 1 dx, and that will be x by 2 plus x cubed by 2 plus x by 4 dx, which is going to be, this you can combine, this is 3x by 4 plus x cubed by 2 dx 0 to 1. So it will be 3 by 4. So this will be 3 by 4 times x squared by 2 plus x to the 4 by 8, 0 to 1. So it's going to be 3 by 8 plus 1 by 8, which is 1/2. So I'm sorry about my initial choice of g. Initially, when I picked the problem from the book, there was no z at all in the definition of g. The original problem was just xy. But then I thought it is better to have a problem where you realize that this g has to be replaced by f of xz. So I thought of putting some z, and the obvious thing that came to my mind was putting a z there. But then your integration gets messier. So then I decided to put something which depends on z, but nice enough so that when I make this substitution, z equal to f of xy, this expression along with the product that you get because of root of 1 plus fx square plus fy square, that product becomes nice. That was the whole idea in making this problem change a little bit. So that is about surface integrals of a scalar valued function. And now let me introduce the flux integral across a surface. So flux integral across a surface. Flux integral of a vector field. So now let us take sigma to be again the set of points x, y, z. It's a level surface of the function little fx. Good. And my xy varies over d. So this be a level surface of function f, and its projection on the xy plane is d. Good, its projection on the xy plane is d. And let us take a vector field on sigma 2r3 be a vector field on sigma. Then we want to define what is known as the flux integral. So f bar dot n bar ds over this sigma over the surface sigma. So this is going to be a two-dimensional analog of what we saw, the flux integral along the curve. So the point is, all you are doing is you are integrating the scalar field f bar dot n bar. So here we are integrating the scalar field f bar dot n bar over the surface sigma. So now note that the outer normal n bar for the level surface z equal to f of xy is given by n bar is going to be minus fx minus fy 1. Because what is n bar? You are taking the gradient of this function. So this is because the surface is the level surface of, I call this psi xyz equal to z minus f of xy. If I take it like this, then the gradient of, so n bar is the outward normal, is given by the gradient of psi, is given by the direction of n bar. Gradient of psi, but the gradient of psi is going to be minus fx minus fy comma 1. So therefore, so n bar is, so this is the direction, so you have to divide by the norm. So note that n bar, the level to the level surface, z equal to f of xy, I should say, is in the direction of that. So therefore n bar is going to be minus fx minus fy1 divided by root the square of these components and add them. So this is going to be your n bar. So therefore the flux integral f bar dot n bar ds would be simply the surface integral of the expression f bar dot minus fx minus fy. I am calling capital F the vector field, little f is the function whose level surface is the given surface. This divided by root of fx square plus fy square plus 1 ds. But this we saw, this is the surface integral of a scalar field. This is the surface integral of the scalar field given by this. But by our previous formula, this is the double integral on d f bar dot minus fx minus fy1 over root of this. But then you are multiplying also by the root of fx square plus fy square. That's your surface dA. So these two terms cancel and you get a formula which is surface flux integral of f bar dot n bar over ds is simply converted into a double integral over d f bar dot product with little fx minus little fy 1 dA. So the flux integral over a surface is a special case of surface integral of a scalar field. And so let's do one problem based on this and then I will stop. So let's calculate some flux integral. So let's do find the flux integral f bar dot n bar ds over sigma, where f bar of x, y, z is going to be x square y I bar plus z k bar, and sigma is the surface of a triangle which one I'm taking, let me think of this for a second. Yeah, so it's going to be x, y, z, where z, x plus y plus z is 1, and the projection and I will say x positive, y positive, z positive. So this is going to be, if you look at x plus y plus z is 1, this is a triangular surface of a triangle which joins 1 0 0 0 1 0 0 0 1. So this is the surface we are looking at. That's the vector field, and so you want to find out the flux across this surface corresponding to this vector field. So here little f of xy, which is z, which is 1 minus x minus y. So fx is minus 1, fy is minus 1. Therefore, the flux integral f bar dot n bar ds over sigma is going to be, now I have to draw a picture of d. This is my d, this line will be x plus y equal to 1. So this will be double integral on this d of the function f bar dot product with minus fx minus fy comma 1 dA. So it's going to be double integral over d. F is going to be given by x square y comma 0 comma z dot fx is minus 1, so this is going to be 1 1 1 dA. So this is going to be double integral x square y plus z dA, and that z is, you are going to replace z by 1 minus x minus y dA. And now you just integrate this thing on the triangle by fixing, say, x first. So I want to integrate with respect to y first. dy and then dx. Y will run between 0 to 1 minus x. X will run between 0 to 1. So this is going to be integral 0 to 1. If I integrate this with respect to y, I get x square y square by 2 plus y minus xy minus y square by 2 between 0 to 1 minus x dx. So this is going to be, let's see what happens, 0 to 1 x square into bracket 1 minus x square plus y goes, I'm replacing 1 minus y by 1 minus x, and so this is just a computation which is painful, but you can do this. So this is going to be x square into bracket 1 minus 2x plus x square plus 1 minus x plus x square minus 1 minus becomes plus 2x plus minus x square by 2 dx. And that's going to be, still need to compute. So I'm going to get x to the 4, then minus 2x cube. That's the only x cube term you have, isn't it? Then you have a x square, another x square, that's 2x square, and plus half x square. 2 and a half is 5 by 2. How many x's? Minus 2x here, and then plus one more x, so you will get minus x, and the constants, which is plus 1 here and minus half there, which will be plus half. So this is going to be x to the 5 by 5 minus 2x to the 4 by 4 plus 5 by 2 x cube by 3 minus x square by 2 plus x by 2. So it's 1/5 minus 1/2 plus 5 over 6 minus 1/2 plus 1/2. So this cancels and you will be left with 16 by 30 or something like that. So we'll do more of this because you need practice, but these are the ideas. You are talking about surface integrals and flux integrals across a surface. That will prepare us to formulate two important theorems. So what's left in the course is two generalizations of Green's theorem in 3D. So Green's theorem was a theorem which we saw last time. In the plane, you have a region and you have a vector field f equal to m plus mi bar plus nz bar. Then line integral of f bar dot dr bar is, if you take a closed curve C, then is equal to dn dx minus dm dy over the region D. That's form 1. You can also write this as flux integral of f bar dot n bar ds. That's double integral of dm dx plus dn dy dA. Now you will see that this in 3D becomes curl of f. This in 3D becomes so-called divergence, which I will introduce next time. And so if you have a surface, now not flat in the plane, but a surface like this in 3D, and this is the bounding curve of the surface, then you will have the same result true. This is called Stokes' theorem, which says that the line integral of the vector field along this curve bounding a surface is going to be the surface integral of the curl of f, the flux integral of the curl of f. And then in this situation, if you have a volume enclosed inside a surface, then the triple integral on the surface equals the surface integral, the flux integral across the surface, and that's called Gauss's divergence theorem. This we will see next time. So at this point I will stop recording and we'll see the next lecture. In the next lecture we'll see the main punchline of this course, which are these two important theorems.